Welcome back, everybody. I can see that we have everybody's already in spring break mode, except for you guys who came here to learn some cool stuff. So today I want to finish up paging and then move on to I/O, and I have some cool new devices I can tell you guys about at the very end. So if you remember, everybody. You remember last time we were talking about the clock algorithm, and basically the way to think of the clock algorithm is you take every physical page in the system, you put them in a huge ring, so you link them together, and there's conceptually a clock hand that moves around every time you need a new page. So you only advance it on a page fault, and what we're going to do, instead of having LRU, which finds us the oldest page, we're going to find for a page that's not young, okay? So in the page table entry, we have 4 bits that are interesting to this. We have the use and modified bits. We have valid and we have read-only. So valid and read-only are really bits that have to do with the demand paging, okay, and with whether something's writable or not. Use and modified are going to help us also with our clock algorithm. Use means that the page has been used recently. Modified means that it's dirty and been modified. And the clock algorithm, the simplest clock algorithm, is very simple. So pages are in a ring, and on a page fault, you advance the clock hand, and you look at the use bit. And if it's a 1, then it's been used recently. You clear the bit. If it's a 0, it hasn't been used recently, and it's a selected candidate for replacement. And what does this mean exactly? Well, if you think about it, because every time we encounter a 1, we turn it to a 0, that means if we go all the way around and come back and we see that it's a 1, we know that it's been used since we put it to 0 the last time and went all the way around. All right? Were there any questions on that? So if you were to look at all the 1s and 0s of the use bit, it's crudely partitioning the state of the system into old and young pages. Yeah. So clock hand doesn't really advance on bringing something in, it advances on kicking something out. So for instance, if you have all 3 pages and you bring in A, B, C, D, the hand won't move at all. It'll stay or wherever it was, yeah. So the hand only really needs to be advanced when you're looking for a page. That's why the speed of the clock hand tells us something about how many page faults you're having per unit time, right? If you have a lot, if it's moving rapidly, either you have a lot of really busy pages or a lot of page faults. Those are usually very closely related to each other. Okay, so so if you look at this, we were talking about this last time, on the face of it, you look at this, you're clearly using all of the bits, right? You need the use bit for the basic clock algorithm. You need the modified bit to know whether the page you're about to kick out is dirty or not, which means you got to take the trouble of putting it out to disk before you can reuse it. Valid, read-only also seem pretty useful, right? Valid is fundamental to the page table entry, and read-only tells you whether it's writable or not. So all of these bits look like they have to be in hardware. Oh, and incidentally, I had a good question last time. What does it mean to say these bits are in hardware? As opposed to being in software. Anybody want to take a stab? What's it mean to say, yeah? Okay, part of the address? No, that's not quite there. What do I think I mean when I say they're in hardware? Yeah. They're in the TLB, but what else? They're managed by hardware might be the better statement. So when you do a load or store, the hardware finds the page table entry and sets the bit to use bit on. So the hardware is doing it. Okay? So it's not only are the bits in the page table entry, I realize that was an ambiguous question, but whenever I read or write a page, the use bit gets modified in hardware, it gets turned on. Whenever I write a page, the modified bit gets turned on. All of that's being done by the hardware, not by anything my software is doing. So as I've described the clock algorithm here, the only thing that the hardware, long night. The only thing that the software is doing here is in the clock hand, we set the use bit to 0. All the rest of this is hardware. If I happen to touch a page, the use bit gets put on by hardware. If I happen to write a page, the modified bit gets turned on by hardware. Okay, is everybody clear on that? Because it kind of makes the, if you're not clear, then the next couple slides get really confusing really quickly. So, we good? Yeah. Yeah, I can repeat that. So, what I mean by these are managed in hardware is that if I touch a page, I do a load or store to a page, the hardware turns on that page's page table entries use bit to 1. If I write to it, the hardware sets the modified bit to 1. Okay? When the clock goes around in software, I'll set the use bit back to 0, but it's up to the hardware to set it to 1. Yeah. Say again? That's a great, so does that mean inside the system call handler? I like the question. The answer is no. It's not even a handler. It's the hardware. There are some transistors that reach out and turn that bit on. No handlers need apply. Okay? Good. Yes?
So why would you use hardware to set the bit to 1 and software to set the bit to 1?
So can somebody give me a good reason why we want hardware to set the bit to 1 and software set it to 0? Good. Yeah, go ahead. Yeah, that's one way to look at it. I think, right, it's about frequency. Whenever I touch a page and it's busy, I'm touching it a lot, and I'd rather that the hardware is busy turning that bit to 1. When I'm about to kill a page by getting rid of it, I'm setting it to 0 in software. Hopefully that's a low frequency event. So it's always good to have the hardware do stuff that may be happening a lot, like turning the use bits on, whereas the software is kind of doing this slow thing, turning them off. Okay? There's a question? Say it again? So all of these bits can be done in software, but I want to make sure everybody knows about what it means to do it in hardware before we go there. Okay, because I realized afterwards that after last time I wanted to make sure that everybody was on the same page. No pun intended. Okay, all right. So we can ask now, do we really need the use or dirty bits? I've just said, yes, we need them to be done in hardware. That's what I just sort of said, right? It seems like the hardware turns it on. The hardware sets the dirty bit or the modified bit. So, no, we can emulate in software, and that's where I was going last time. So basically you keep a software version of these use, dirty, valid, read-only bits, and then, and the reason we need to keep valid and read-only is for the subsequent parts of this, and we're going to start by marking every page invalid whether or not it's actually valid. So we're going to keep the notion of valid or read-only in our software structure, but in the hardware we're going to mark it as invalid by setting the P bit off in the page table entry. And if we do that, what do we know? Every time we do a read or write to any page after that, what happens? If every page is marked invalid and I do a read or write, what do I know is going to happen for sure? Page fault. Which means the software takes over. And at that point, if it's a read fault, what I can do is I can set basically the page to be read-only and mark my little use bit to 1 in software. So this said, because I don't have hardware to do this, I'm going to have a handler. I'm going to set it up so that when you go to do a read, causes a fault, goes into the software, and now I'm emulating or faking it by having my own use bit in software for that page. And similarly on writes, I basically go in there, and not only do I turn the use bit on, but I turn the dirty bit on in software. Okay? And when the clock hand advances, instead of looking at hardware bits, which we don't have, I look at the software ones, and all the same stuff works. And basically, when the hand goes along, and if I decide that a page is busy and not going to be thrown out, then I once again mark it invalid, turn off my software bits, and the next time somebody tries to use it, I'll get a fault. Okay, so what this is this is a way of causing the operating system handlers now to take over when we would have had hardware do it for us. Now, you can imagine you really want hardware because it's faster, but if you don't have the hardware, do it this way. Okay? Good? Now you can remember, though, if you think this through, it seems like there's a lot of page faults, which are entries into the kernel, which take time. Maybe we'll want to do something better. And to do that, we can remember that the clock is just an approximation to LRU. So maybe we could do better than a clock algorithm with emulated use in dirty bits. Maybe we could do better. Okay? And there is a very famous architecture, the VAX from Digital Equipment Corporation, that indeed didn't have a hardware use bit. Okay? And so they had to do something else. And so they came up with this thing called the second chance algorithm, which has the same goal as the clock algorithm. The goal of the clock algorithm, approximate LRU. The goal of this algorithm, approximate LRU. Find me an old page, not the oldest page, right? So here's what this looks like. We divide the pages into two halves, green and yellow. Okay? Green pages are all mapped and ready to go, and the processor reads and writes them, and then, nobody notices because everybody's happy here. The yellow pages are pages that represent pages that are part of the process, but they're mapped invalid. So even though they're in memory, we mark them in invalid, and anytime we read or write them, we're going to get a page fault. But since they're ready to go, then we could change the bit to, read only or read write, and they become green and we could use them. So these are not, when we get a page fault on the yellow ones, they're not red, they're yellow, which means it's not going to take a long time. I just got to pop in there, change a few bits around, okay? The green pages, I don't have to do anything with because I can just read and write them. Now, the thing to remember about this is when something's green, the loads and stores are just happening, and so nobody's getting any events. There are no handlers that are being called when a read or write happens on the green side. Unless you do a write to a read-only page, then you'd get a fault. Let's assume we're not doing that for a moment. So what does that mean? That means if I want to approximate LRU, the green pages are not going to be part of that approximation because I'm not getting any information about how frequently anybody's reading those pages or what's happening because they're just there, right? They're being used. So what we do is, since I don't have any better information, I'm just going to manage these guys FIFO so that, when I put a new page into green, I take out the oldest one. And I'm just going to manage those FIFO, but I'm going to get my approximation to LRU by what I do with the yellow ones, okay? And so, basically, if I access pages in the active list at full speed, nothing funny happens. If I get a page fault, either because the page is not in memory or because it's over here, what am I going to do? Well, I take the oldest green page and I put it on the yellow side and mark it invalid. So I moved it over there. And now I take that page that I just, let's say I page faulted because there was a yellow page I wanted to use. I conceptually bring it over to the green list and mark it usable, and now I can start using that page. Okay, because I take a fault and go into the kernel to do all this management of yellow, I'm going to make my yellow list completely LRU in the true sense of the word. I'm going to sort it as a list. So I know the oldest page there. I know the newest page there. Okay, so what I'm showing you here is a page fault which grabbed this page, put it over here, had to get rid of an extra page in the green, put it over on the end of the yellow page, and now that is sort of LRU, because whenever I move something over to the yellow side, I'm managing it LRU, and it's only these green ones that are just kind of anomalies in the LRU-ness. Question? Yeah.
So let's say you're in green, and then you hit a page fault in the yellow part.
Good. So what about a page fault not in the yellow part?
It seems to be very expensive.
No. Well, it's no more expensive than a page fault in the clock algorithm that's not in the memory either. You got to go to disk, right? So what am I going to do with disk? Well, in order to go to disk, I'm going to pull a page off the disk, put it in the green list so it's active, and I got to kick another green one out. So in that case, rather than grabbing a page from yellow over here, I'm going to grab a page from disk put it down here and kick one out of the LRU list because I need spare memory. And in that instance, that's the oldest page that we know about in the system now, because nobody's used it. It hit the end of the LRU list. Okay? No, because this is a list. So all I have to do is take the one off the end and put a new one on the beginning. And I'm using a linked list. So I don't actually have to increment anything. And I'm managing it in software. Remember the problem with LRU list before when I said, wouldn't it be great to have true LRU? The problem with that was every load and store was rearranging these pages on the LRU list. Really expensive. The only time I rearrange pages on the LRU list here is when I either do a page fault, really expensive, or I will page fault off disk, which is really expensive, or I pull something out of the green to the yellow, which is also certainly a little bit more expensive than a load or store. And so it's not too bad. Okay? This is an honest-to-goodness real algorithm that the VAX folks at Digital Equipment Corporation came up with as a way of approximating LRU instead of using clock because they didn't have a use bit. Okay, so rather than emulating a clock algorithm that works better with a hardware use bit, they said, well, let's do this instead. And it's got its LRU-ness to it because of the yellow side. And in fact, if you think about it, if I had only one green page, I'm not going to recommend this, but suppose I have only one green page, then it's really LRU. Right? Really, really LRU, but every load and store pretty much causes a fault in and manages the list. In fact, I could have 0 green pages, but that would get too confusing here on this slide. If I have all green pages and no yellow pages or one yellow page, I basically have total FIFO. And then, of course, we run into Bilaty's anomaly, right? So that wouldn't be too desirable. So something is somewhere halfway between green and yellow seems good here for LRU-ness. Right? Okay? And how many pages in the second chance list? Well, if there's no pages in the second chance list, we've got FIFO. If they're all there, we've got LRU, but a fault on every page reference. I can tell you this is probably too expensive, and this one has weird anomalies, so somewhere in the middle. Pick an intermediate value. And the pros of this scheme is it's, fewer disk accesses than other ones. This is basically closer to what the clock does from disk accesses. The con is a little bit increased overhead, relative to the clock algorithm, but not so bad. And we can also adapt to all sorts of kinds of access patterns in choosing where things go in green and yellow. But that's another story for later. So the question that you might ask is why the VAX didn't have a use bit. Streckler, famous architect for Digital Equipment Corporation, said, hey, OS people, do you need a use bit? They said no. And, he later got blamed for not having a use bit on this architecture. Wasn't his fault. Okay, so architects of the world unite. Wasn't his fault. Okay. Questions? Yeah.
So where on the yellow pages stored a system managed by the kernel storage them?
So first of all, you could ask, maybe you're asking the wrong question where they're stored. They're in physical DRAM. The kernel is managing them. The user program has no access to them because the page table entry says invalid. Well, but yes, but the kernel is got to allocate memory in the clock as well because the clock has every page of the world in it. So this is a way of managing the physical pages. Good. Okay. We good? This is the second chance list. So now what's interesting is, of course, those of you that thought a little harder or a little ahead of this says, well, this is kind of bad because every time I got a page fault, I need an immediate page, and so I got to run the clock algorithm. Well, in fact, what really happens is you got a free list, and the clock algorithm runs to keep the free list full rather than when you need a page. And what's nice about this is if the free list needs a page, you sort of advance the hand, you put stuff in at the top, and once it gets onto the free list, if it's dirty, you start it going out to disk. so that by the time it gets down to the front of the free list and you're ready for a page, you've got basically a clean page that you can use. And so there's typically a page out daemon or something that's running in the background, actually running the clock algorithm and trying to keep the free list free enough with enough pages on it that whenever you have a page fault, you just grab the one that's at the head of the free list. Okay? And this is kind of like a second chance list almost, because if, while something's on the free list, you get a page fault that says they need it, you put it back into the clock. Okay? So these green ones, unlike the green ones on the previous slide, these are actually unmapped or they're invalid to the user. So if the user tries to use them, you get a page fault, you put it back at that point. So it's like a second chance list, but it's being used as a free list in this instance. Okay. Very good. Faster for a page fault. And we have a way to say, okay, well, I'm on the free list. I'm about to get kicked out. Let me start getting my dirty pages out to disk. And so by the time you actually get around to reusing it, there is no dirtiness to it, and you can just reuse it right away. Okay? Now, physical page frames. Here's a detail that's kind of interesting. Physical page frames are often used by many different processes. What do I mean by that? Think about it for a moment. If you take a parent and fork off a whole bunch of children, they all have pointers. All of their page tables point at the same physical pages, right? Until they start modifying them. Well, that means one physical page, many page tables. So how do we even manage this? Because, if I got a clock and I want to mark a page as invalid or whatever, and I want to get rid of it, I got to hunt down every page table that page is in so that I can invalidate it in every page table. So that requires a little work. That's often called, that reverse page mapping is also often called a core map. And it's got to be there because you know that one physical page in many page tables, and when you're ready to move the physical page out to disk, you got to hunt it down. And so that's what the reverse core map does. Maps from physical page ID to every page table it happens to be in. Okay? Many implementation options. You could imagine that you could do this on every page, so that could be very expensive. In Linux, in fact, what actually happens is ranges of physical pages are treated together in a way that allows you to do this reverse core map on ranges of pages instead of on every page, and it's a lot cheaper. But the basic idea here is pretty straightforward. Okay? Questions? Good. So let's talk about a couple of other interesting things here. So how do we allocate memory amongst different processes? This sounds like a scheduling question. Does every process get the same fraction of memory? Seems plausible. Or should some processes get completely swapped out to memory where all of their memory gets pushed out to disk and they have no image left in core? Okay? How would we even know? Well, every process needs a minimum number of pages so that when it gets the CPU, it can run a little bit. Okay? So any process that's actually loaded into memory, we make sure that it has a few pages, like, 3 or 4. We could figure that out by what instruction set it's got, but enough that when we give it the CPU, it can actually run without an immediate page fault. Otherwise, what's the point of having it in memory? Okay? And so if you were to look at things like the IBM 370, you might actually need 6 pages maximum for a move instruction. Okay? Every processor is going to have a minimum number of pages to let every instruction at least run once. And so you could figure out how many pages that is. It's a small number. It's a little silly, however, to keep a process having only the bare minimum number of pages. So it's basically never done, right? You have enough pages based on some threshold so that it can always run. And then we can say, okay, if we need a new page and we're going to kick out a page from somebody else, who do we choose? Well, one thing is we could treat all the processes together in one big heap of memory and just do the clock globally. That's what we just kind of talked about. Pick the next one that's free. Okay, that would be a global replacement scope, and that's very common, by the way. Lots of operating systems do that. The other alternative would be a local replacement scope, where every process has a fixed number of pages that it's allowed, and when you go to get a new page for your process, you have to kick out one of your own pages for sure. Okay, that's why we call it a local scope. Okay, so the clock algorithm is like a global scope. The local scope says that I'm doing kind of like the clock per every process if I wanted. All right. And I could do this in many ways. I could split it up equally, so every process gets the same amount of memory. I could split it up proportionally, where the larger processes get more memory based on some fraction. Can anybody tell me why this is probably a bad scheme? Sounds good in theory. Give the bigger processes more memory proportional to, yeah. Yeah, you link in 12 million different libraries so that you've got the biggest process ever, right? And as a result, you get a lot of physical memory. So this one seems like you could game this one, right? Just because you have a lot of memory doesn't mean you need a lot of memory. You'd like it to be based more on how much you're actually using. You could have a priority allocation, just like we talked about schedulers. Maybe certain high priority ones take away from low priority. All of these are used in various ways. The last one I want to tell you before we move on is maybe we should use some sort of adaptive scheme where we figure out which processes actually need memory and give the memory to them. Okay, and how would we even do that? Well, we could try to reduce capacity misses by dynamically changing the size of memory for a process. So we could do this. So here's assuming we don't have a Bilaty's anomaly problem, okay? We could say for this number of frames given to a process, here's the number of page faults. So presumably, as we add more pages to the process, we get less page faults. That's hopefully true. And notice how we might have a lower and upper bound. So if we're too far below the lower bound, gee, this thing has too many pages. If we're too far above the upper bound, gee, this thing has too few pages. We could dynamically give more pages or less pages to a process based on where they are in this page fault graph. Okay, so that's dynamically trying to adjust the memory usage based on how much it's actually taking. Okay. Now, what if we just don't have enough memory? Okay, that leads to what's called thrashing. Now, I know you've heard thrashing many times over the course of your career here at Berkeley. I wanted to give you one option here to think about it. So as we add more and more processes or threads, we can keep the system more and more busy. Because some of them are waiting for I/O and so on, up to a point when the overhead of having all of those threads running simultaneously becomes so much that our utilization of the CPU starts dropping to zero. Okay, why would this happen? Well, because all of these processes are working so hard that they're causing swapping all the time, and we're doing we're always going to disk over and over again, and basically nobody's making any progress whatsoever. We're thrashing. So there's this curve I showed you earlier. This one has no happy solution for the set of all processors. There's no way to take the set of all processes I've got running and give each of the ones that have too much faulting enough memory to get them below the high level bound. And basically what's happening is they're all just faulting all the time and nobody's making any progress. That's called thrashing. Okay, and what's the best thing I can do under these circumstances? If I've got so many processes running simultaneously that I'm just thrashing and nobody's making good progress, what do I do? Say again? How do we reduce the number of processes? You could kill a couple of them. What can we do that's less drastic? Queue them. How? Okay. Anybody? Okay. What's the equivalent of queuing? Yeah. What was that? Priority. Okay. Yeah, we could give them priority. Yeah. Do what? You could make them run really slowly, but they're still going to cause page faults because they're going to have a working set. So what we could do is, let's ask this question. How do we detect this, and what do we do in response? Yeah, you had a thought?
I was thinking you could change your scheduling algorithm to be just like running multiplication for each process.
So we could change the scheduling to FIFO-like. Sure. What else could we do? How about this? We could push a process entirely out, put it on disk and don't let it run for a while, and then come back. So that's freeing up all of its memory. Less drastic than killing it off, right? But first of all, we might want to figure out when we're thrashing. And so if you remember, I told you a while back that if you were to look at the addresses running in a given process, you'll see that at any given time there's a working set. Okay, that's the group of pages currently in use. So like right here, if you see this is the working set, all of these things where you see total blue, those are addresses not in use. Really, what we know about thrashing is if we can't get the working set of all of the active processes in memory at the same time, then we've got thrashing. Okay, so the working set kind of defines the minimum number of pages you need for the process to behave well. So not enough memory for the sum of all the working sets give you thrashing. And at that point, it's probably better to do this swap out. So swapping out a process means put all of its pages on disk and then schedule it later, okay, as a way of freeing up the other processes to make some progress. Okay, how do you make that decision? Probably priority or something. Okay. So there is a working set model. So you pick a window, fixed number of instructions like 10,000 instructions, and you want to have it sort of this delta just big enough to sort of encompass the current working set, but not too big, otherwise you got the whole program. That working set model, you sort of sum the total demand of the frames for all of the working sets for all processes. That tells you how much memory you need for all the processes currently in core to run. If it's too big, you got thrashing. So this is just a way of formalizing a little bit this notion of working set, which is I look at the last, say, 10,000, pick a number, references, look at all the unique addresses in there. That's maybe my working set, and it's a sliding window over time. And what's interesting about this working set model is people have any questions on this? It's just a mathematical specification of this previous idea here of how many gray pieces do we have in the current blue bar? Everybody with me? How many addresses currently in use in the current blue bar? That's what this is saying. If we do that, we can start solving some interesting problems. Like one, we know when we're thrashing because we've got our working sets are too much. But how do we get rid of compulsory misses? Prefetching, yes. So we could cluster together pages that are related and prefetch them. Like, for instance, all of the pages that are after a given one in the program code space, we pull in at the same time if you touch one. Another interesting thing is we could track the working set. There's actually, Windows did this for a while, one of the versions. You track the working set, and when you bring the thing back in and start running it, you pull its current or its last working set back in at the same time as a form of prefetching to get it back to where it was when you stopped running it previously. So these are ways of getting after compulsory misses. Okay. So before I do this, I'm going to talk about, let's give you guys a brief break. We'll get back to that. So administrivia. So I wanted to say something. I mentioned the zero-sum game for the projects a little while back, and I had a couple of people misinterpret what I said. So let me restate this. So, for one thing, we forgot to put up a metric, which I really want. So we're going to give you a second metric, which is you guys get 20 points for each of your partners, and the trick is you get to hand out the total of that to your partners, not to yourself. The evaluation is not about yourself. The evaluation is about your partners. Okay, I think we had a few people that had the mistaken notion with with only the metrics we put up, that if you give all your partners a 1, you somehow give yourself a boost, okay, on the project. All right? That is absolutely not the point. Okay? The point is not, in fact, we had somebody say this is like a Hunger Games for operating systems. Okay? No. Not like that. The idea here is you're evaluating your team, how they're doing. They'll evaluate you as part of this. And then we're going to take the sum of what you get from your partners and so on, coupled, of course, with reality checks by your TAs, right? So, we ought to make sure that, the TAs have a lot of input on this to figure out what's going on. So I wanted to remove the notion of Hunger Games. It was a fun set of movies, but it's not what we do here in 162. This is about evaluating your partners. Okay, don't, just watch for this. We're going to have this out. We're going to do this for projects 2 and 3 too, okay? This is the way I normally do this, and I didn't realize that what we set out didn't have this crucial component. You're evaluating how your partners are doing. It's not about giving yourself a boost by telling they all suck, I'm great. That's not the point of this, okay? All right. All right. We good? All right, and everything, yes. How much does a point represent in 60 total points? 0.016. Now look, think of it this way: if you want to if you're equally happy with all the partners, that's 20 each, right? Then you can adjust. The nice thing about 20 points is it gives you a lot more granularity, okay? And try to be honest about this. And we're going to validate them with the TAs, and this, this is about trying to figure out how your team dynamics are going. It's one of many metrics. Okay, and the other ones, which were the 1 through 5 numbers, are going to be used by the TAs in helping to validate their ideas. But these numbers, these are ones we might actually use for a very initial quantitative approach to this, completely modified by TAs. But try to do this, okay? And don't think Hunger Games, think reality. What are we doing with our partners? How well are they working? Okay, and if anybody's concerned about this, talk to me in person. But this is not about marking them down to get better stuff for yourself. Doesn't work that way. The other thing is the midterm survey. Not about the midterm itself. This is the survey. About halfway through, the term is up. A lot of people have already put down their evaluations. That's great. We're going to take a look at them. We always like to do this to get an idea how we're doing and what we can do better. So please do that. And then the last thing is midterm 2 is the Thursday after spring break. So don't lose everything in your brain, open brain, lose contents next week. And we will have a review session coming up on Monday, and it's going to be posted on Piazza. Okay, any administrivia questions? Okay, are we all breathing deeply and we're ready to go for spring break, which is going to be awesome, right? Okay, great. Now, let's go back. I want to talk about Linux for a moment, and I want to talk about something that's very timely. So, memory management in Linux, which is a real operating system that's used by lots of people, is considerably more complex than the examples we've been giving. Okay, for instance, there are a bunch of memory zones, like there's zone DMA for all the memory, physical memory less than 16 megabytes. That's totally historical. Because it used to be you could only do DMA in those regions of memory. We'll tell you about DMA in a moment. We have zone normal, which is 16 megabytes to 896 megabytes. We have zone high mem, everything else. Okay? And every zone has one free list, 2 LRU lists, an active and an inactive one, and they swap. Okay? Many different allocators. There's one called the slab allocator, which sometimes I talk about. We don't have time this term to do that, but it's per page allocators, mapped, unmapped memory, all sorts of interesting stuff. There's many different types of allocated memory. Anonymous memory is memory that's not backed by a file, but it's going to be backed by the swap space. There's mapped memory, which is actually mapped by a file. So mmap is something we'll talk about probably next time, and they're going to talk in section as well. There are allocation priorities of various types. Okay, so this is, if you were to actually look at the memory allocator in Linux, you'd see there's some pretty interesting details in there. Some of them historical, some of them not. This is the memory map that you see in Linux, and I say this is pre-Meltdown, where Meltdown is what happened last year when it became clear that you could steal memory out of a kernel despite the best attempts of a good kernel, and we'll talk about that in a second. But the way the typical 32-bit memory space was, the bottom bottom 3 gigabytes was user, and the upper 1 gigabyte was kernel memory. And the way this worked, first of all, was when you were in user mode, the red addresses were not available. They were in the page table, but the fact that you were in user mode meant that if you tried to access them, you'd get a page fault, segmentation fault, okay? The green ones were good. Now, why would you bother? But up in this memory, for instance, all of the user's physical pages, up to 896 megabytes, were mapped directly in kernel space, okay? Now, why would I want all the kernel, and the kernel space was up there too, why would I want kernel and user in the same address space, let's say, in the kernel? So when I go into the kernel, the red ones suddenly become available. Why is this useful? Yes? Yeah, so think about what a system call does, right? You do a system call, you go into the kernel, and now the kernel's got to read, the user memory because there are arguments in there. It's got to do stuff. It writes stuff back to user buffers. This makes system calls and other times you go into the kernel much simpler if the kernel can say, hi, I'm in kernel mode, and suddenly it's got access to all the user's pages and all of its pages. Okay, it just makes it much easier for the kernel to do what the kernel does. Okay. Now, by the way, when you get to 64-bit address space, there's all sorts of cool things that happen, mostly because a lot of processors like the Intel ones don't even allow you to have addresses that are 64 bits in the virtual space. So what really happens is you typically have what's called the canonical hole, and there's a lower part of the address space and a top part of the address space. And if you notice, there's a certain number of bits, like 48, where the very top bit here is a 1, and the top bit in that 48 here is 0. And then they're mirror images of each other. And so those are the only virtual addresses that make sense. Okay? And so then typically the kernel stuff is up top, and the user stuff is down below. Okay? Now, kernel memory is not generally visible to the user. Okay, there is an exception, which is dynamically linked shared objects, which float around up there. We won't go into that. Physical pages are described by a page structure. So how do you make a clock algorithm? Well, you take every page structure and you link it in a linked list, and now you got a clock. Okay, and that's kernel memory that points at the physical pages. For 32-bit virtual memory architectures, when you have less than 896 megabytes of physical memory, then all of the memory is actually mapped again up top. So regardless of where it is in the user space, the kernel can get at it easily. And then there's some craziness when you've got a lot of memory, which of course we know is where everybody is now. But everybody's also got 64-bit architectures, and so all physical memory in the system is echoed in two places. One where the user's got it, if the user's got it, and up top the kernel's got every physical page available up in its upper virtual space so it can manage it. Okay? So, this is fine. Things evolved this way over many years. People figured out how to do system calls really well, and then Meltdown happened. Dum-da-da-dum. And so the problem with Meltdown, in a word, is when you're in user mode, despite the fact that the red things up there are not available to the user, but they're in the page table. What does that mean? You're user mode, you try to access them because you're not a kernel. Even though the page table's valid, you still get a page fault because you're the user. If you lay the memory out that way, then it's possible for a malicious user to read stuff in the red space, even though the processor says you can't because the page table says you can't. Now think about that a second. That says that even though we set the page table to be only readable by the kernel, the user can read it. That sounds bad, right? How many people think that sounds bad? And that's bad. And a lot of a lot of people were very surprised by this. So this is not Intel made a bug. This is 20 years of computer architecture with out-of-order execution caused a weird hole to open up that wouldn't technically have ever been considered a bug in the past. Okay? So if you were a computer architect, what you would find is that anybody who tried to access kernel memory in this picture would get a page fault. That works. What's the problem? Except that if you're clever, okay? And here let me show you how clever you can be. Okay, now, if you were taking 152, you'd learn about out-of-order execution. And speculative execution. We're not going to go there too far, except for the fact that what I'm going to tell you is speculative execution says, in order to make things fast, I'm going to go ahead and do things that I don't know whether I'm allowed to do yet, and I'll make sure that when I finally figure out whether I can do it, then I'll squash it before the results go into a register. So a good example would be, I could try reading from the read space, and maybe the read will go through and start into part of the pipeline, but before that value actually gets to a register, the exception will happen and it'll all be squashed out and everything's fine. Okay, because, yeah, I did it, but then I didn't let you find out what happened. Seems good, right? Here's an example of why it isn't good. So look, and I'm just going to give you a rough idea, but it's pretty crazy, okay? So the idea is I've got an array here of 256 entries times 4K, and the 4K is kind of a side effect we can talk about. I'm going to flush it from the cache. Absolutely not in the cache. And then I'm going to do like a try-catch, which you can do in C with some weird combination of catching the sig-seg-the signal, which you guys all know how to do that, and set jump, long jump to get something like a try-catch. The simple idea here is, look, in here, I'm going to try to access a kernel address I'm not allowed to. I'm going to put the result in result. And then I'm going to immediately take that result, which is just a byte, 256 values, and use it to load from the array into a dummy variable. Now, this array is in user memory, so this is perfectly valid. Result is one of 256 values. And so when I load into it, that's perfectly okay. Okay, and then later, the fact that I flushed it here and one out of 256 values came back and I used that to load the array means that one entry in that array is fast because it's in the cache and the rest of the entries are slow because they're not. Okay, now, ignore for a fact that this is illegal. We'll get to how it happens. Suppose that that was actually legal. I want you to understand that first. Suppose that this was actually okay. I flush this out of the cache. I load from the kernel address. Say it's okay. It's now one of 256-bit values. I use that to load from an array. Now this array value is cached. So now the last thing I do is I just scan through 256 entries in the cache, and I find out which one is fast. And the one that's fast is the one that got loaded on line 6 because line 5 brought that 0 to 255 value out of the kernel. Everybody see how the timing bug works there? That's a timing channel. And why does this work even though the kernel address is illegal? Is because of speculative execution. What the processor, Intel, and several others do, IBM Power, ARM, is they go ahead and do this access while it's checking whether it's okay or not, because it's going to do this while it's checking the TLB. And before the TLB gets checked, it goes ahead and it does this array load. And then it eventually says, oops, you're not allowed to do that. But the damage is done because the array has already been loaded from memory. Now, you're never actually able to look at result, but the array has one fast entry in it which tells you what the result was. So even though the speculative execution squashes out the pipeline and doesn't let you see result, the array has the answer in the cache by speed, not by value. Ouch. Okay, and you can build something like this and you can drain all of the kernel memory using this. It takes a while because you're doing lots of faults, but it's doable. Okay? Question? Yes? So you could, no, you could not fix this by making sure the kernel pages are not cached because the kernel isn't going into the cache. The kernel address is going into a register, and this is regular user memory. So that one doesn't fix it. So the only way one way to fix this, which is the only main patch, is you get rid of kernel memory being in the same page table as user memory. Then this doesn't happen. But that means when you go into the kernel, and now you got to change from the user's page table to the kernel's page table. And then when you come back, you change from the kernel's page table to the user's page table, which means what? Flush the TLB. You guys all remember that from last time, right? So that means every system call has 2 TLB flushes where you flush everything out, unless what? You have tags in the TLB. Okay, now, a lot of modern processors have tags in the TLB, but unless you have, for instance, Linux 4.14, they don't use them. Okay, and a lot of virtual machines still don't use the tags. So if you've got protection against meltdown, things are really bad. Look, you get 800% overhead in execution because of this double flushing of TLBs. So that's a patch, and they do exist. The real fix is better hardware without these timing bugs, but they're still kind of on the way. So there you go. Welcome to Meltdown. Question? How is that what? How is reading kernel memory bad? Because the kernel memory has got all sorts of private stuff in it, like files that other users have, or maybe passwords in other people's process space. So the kernel memory, the reason it's protected is because you're not supposed to know it as a user. And, this basically shocked everybody. What's interesting is ISCA, the International Symposium on Computer Architecture, which was early last year, had a seminar by Dave Patterson from UC Berkeley, Hennessy from Stanford, who won the Turing Award. And they talked about how this kind of thing took everybody by surprise. 20 years of computer architecture blown away by the fact that speculatively executing could be turned into leaking information with the right use of a cache. And they said, look, we don't know what we need to do. We need some new architecture 2.0 thing that somehow takes timing channels like the cache into account and so on. So it was kind of a call to arms, but it was, I think this was a big shock. And this is, by the way, only one of many problems. There's also the Spectre bugs. This one is kind of easy to figure out how to patch. The Spectre ones are much more complicated, and even secure enclave computing got broken. So there's a lot of bad stuff happened last year for computer architects. Fortunately, people have mostly patched everything, but probably not necessarily if you're using virtual machines. They're still not necessarily patched. So. All right, let's take a break. We'll come back and we'll move on to I/O. Actually, I'll leave this up if people want to stare at it while we're on break. One is fast because it's in the cache, and all the other 255 are not, so you know exactly which byte is loaded to the kernel. Well, because you're counting through, you're looking at the array, you're looking at entry 0, 1, 2, 3, 4, 5, suppose that entry 5 is fast, so you know what came back to the kernel was a 5. So you're getting access to the byte from the kernel not by looking at the register byte, but by looking at where the cache is at. Well, no, you load the 5 from the kernel, and then that 5 gets transformed into the fact that entry 0, 1, 2, 3, 4, 5 is loaded into your array. So now when you go through the array and figure out which one is fast, 5 is the fast one. So you know that the 5 came back to the array. No, 5 comes back from the kernel, and then you do this load from the array, and as a result, and that says that whatever the value from the kernel was, speculatively, I'm going to load a 5 into the array. And then all of that is squash. You're never actually able to look at the 5, but you are able to find out that entry 5 in the array is speculative. Because the load into the array wasn't squash. You're loading part of a user's array, so there's nothing wrong with that. But what is squashed is the kernel load. Yep. Question? Because result is not going to be allowed. that's going to be squashed. So before it's squashed and restored to what it's supposed to be, I'm going to go ahead and use it to index into an array. That will also speculatively start going. So the assumption is the result is okay to get, and therefore this load in the cache is going to be okay. But when the speculative stuff is squashed, we only squash the registers. We don't change the cache back the way it was before the speculative. And then we also speculatively load from array, and then when we squash that try catch, we don't restore the array. We do restore the register that would have resolve. So resolve doesn't get to know what the kernel is, but the cache doesn't get changed. Because the cache isn't loading. Technically, you could say the cache isn't loading anything illegal because it's loading from the user space, so that's fine. Well, the array before is flushed out of the cache. But it doesn't matter what's in the array. The array is flushed out of the cache, and after this happens, one entry is loaded into the cache, and I go through it and figure out which entry that is by time. Because you figure out for every entry you try to load what the cache is in the cache, it rolls into the cache. All right. Good. So, yeah, Meltdown was very surprising. So let's change gears to I/O. So, so far in this class, we've learned how to manage the CPU and the memory, but what about the I/O? I mean, without I/O, basically computers are useless. They're like disembodied brains or something, right? But you got thousands of devices, and everyone is slightly different. And so the question is, how do we standardize the interfaces to these devices? Very important. And devices are unreliable. You get media failure, transmission errors. How do we make them reliable? So if you remember the very first day, I talked about this virtual machine view where we wanted to give a view to the programmer of something that was more stable and more reliable and exclusively owned to the user. We call that kind of a virtual machine, despite whatever's underneath the covers, despite the fact that there's one memory shared by a bunch of processes, that there's one CPU shared by many threads, etc. We want to somehow give a good view of I/O, and also deal with the fact that we have many different types of I/O. And so somehow the I/O subsystem, as you might imagine, is actually the most complicated part of an operating system. In fact, if you look at the cause of all the crashes of operating systems, at least, I forget the number, but at least somewhere between 30 and 60% of all crashes are caused by a device driver or other I/O problem. It's awful, okay? Closer to 30, but it's pretty bad. So if you remember, we also started at the very beginning. We talked about sort of pulling things out of storage into memory, dealing with networks into memory. And so now we're kind of going to look at what's below this protection boundary. What are all these buses in some sense, and what do we need to do to manage this in a way to give us a nice, clean virtual machine? So in a picture, we've got processors that would have their L1 and L2 caches. We've got a bunch of L3 caches that are shared. And then we've got the ability to read and write DRAM, storage devices, disks, read and write I/O controllers, all of this stuff. And everything that you recognize that you're used to using that isn't a CPU is an I/O device with some I/O controller controlling it. And processors access the I/O controllers by reading and writing I/O registers as if they were memory. So let's talk a little bit about the interface between a device driver in the processor and a device. What's in between? Okay? So we can ask ourselves, what are some of the parameters of this I/O? So we could talk about, are we accessing a single byte or are we accessing blocks? So some things put a byte at a time, like keyboard, right? When I type a keyboard, I'm getting one character at a time. Others give you whole blocks, like disks. Okay, so dealing with byte versus block devices are going to be important. We're also going to wonder about access patterns. So sequential I.O., very common for things like videos, right? That's clearly you start at the beginning of a file and you work your way through sequentially. Random might be a database where you have to grab things in random order. Okay? Some devices have to be monitored continuously. Others generate interrupts when they need service. How do we transfer from the device into the processor? Okay, programmed I/O, DMA, etc. So if you were to look inside the kernel, you'd see something like this. You're used to the system call interface now. That talks into a kernel, which is basically blue here, and there's a bunch of management subsystems inside of a kernel. So, for instance, there's the concurrency and multitasking. Okay, we've been talking about this a lot, so hopefully this is extremely familiar to you. Memory management, that's also extremely familiar to you now. But what about the rest of this stuff, like file systems? Okay, we're going to have a bunch of different types of file systems and a bunch of block devices, different types of disks, USB sticks, etc. We're going to talk about serial devices like keyboards and kernel and screens, etc. Okay, and also networking, which can be very important. So we have a lot. The other three subsystems are kind of ones that we haven't dealt with yet. Okay, and that's where we're going. So, by the way, there's a lot of kind of interfaces down at this level, which is going to be interesting, which kind of goes between the file systems and interfaces down to the device drivers, and that's going to be something we have to talk more about. But what's the goal of the I/O subsystem? Well, the goal is to give a uniform interface despite the fact that there's many wide-ranging different devices. Like, for instance, this code, now that you're familiar with it, kind of works no matter what something is, right? I fopen dev something for read-write. I go to a loop and read from it. I close it. That file descriptor could be a file. It could be a socket. It could be whatever. And part of the reason is that /dev is commonly a place where you can get at the raw versions of devices. And so /dev/something is actually potentially a device that you're accessing raw. And the code that controls the devices has a standard interface, device driver interface, that you can use this via this interface. And what we're going to do in the kernel is we're going to figure out how to handle different devices giving it the same interface. And we're going to get a flavor for what's actually involved in controlling devices for the rest of now and after we get back. So we want standard interfaces. So one type of standard interface is a block device, which I mentioned. So things like disk drives, tape drives, DVD-ROMs, etc. Basically going to access blocks of data. How big is a block of data? Probably 4K. That's always a good answer, right? Commands include things like open, read, write, seek. Potentially we could have raw I/O or file systems. So you can actually get at a disk drive by doing a raw open, which gives you all the blocks if you're kernel mode, or you could open a file in the file system. Okay, there's lots of different ways to get access to it. And even more interesting, perhaps, if you haven't done this yet, is you can take a file and map it into memory with mmap. And now, rather than reading and writing a file, you can actually read and write memory, which causes the file to be read and written. Okay, so all of these things are possible with block devices. Character devices are things like keyboard, mice, serial ports, USB devices. Single character at a time. Typically, the system calls like get and put are what you're using for that. And there's lots of libraries layered on top for getting lines and so on. And then network devices, things like Ethernet, wireless, Bluetooth, etc. And these are different enough from either block or character devices that typically we think of them separately. And Unix and Windows and a bunch of other operating systems all have socket interfaces to network-type devices. And they help separate the network protocol from the operation, and in many cases include a select option, which is a way to basically say, here's a bunch of network sockets I'm listening on. I want to wake up as soon as any of them have any characters coming in. And so here we get pipes and FIFOs and streams and queues and mailboxes, and all that stuff is down at the network level. So these three types of devices, blocks, character devices, and network devices, are pretty standard across a bunch of operating systems, and they represent kind of different classes of device drivers and different classes of device management. Okay, questions? Yeah.
So even the character devices, they have physical character type, but don't they also have buffers that will store older?
Yeah, so that's a good point. So character devices often have FIFO buffers in and out to them, yes. But the fundamental interface to the raw device is kind of a character at a time, whereas the fundamental interface to a block device is a chunk of 4K at a time or whatever. Okay? Good. So how do we deal with timing? So we have several different ways of reading or writing. So you're pretty much familiar now with blocking interfaces. What that really means is when I do a read system call or a write system call, I get put to sleep until the system can handle my call. Okay, I do a read, I give it a buffer. What happens? It goes to sleep until, say, the socket comes back with enough data, or goes to sleep until the file comes back with enough data. That's a blocking interface. That's what you're used to if you just use read and write without any changes. Another idea is non-blocking. Okay, you can build a non-blocking, or you can ask a file descriptor to be non-blocking with an IOCTL call usually. And what happens is it returns very quickly from a read or write request with however many bytes it can give you now, but it may not be all you asked for, and it never waits. So when you do a non-blocking call, read comes back immediately. You might get 0 bytes, but it will come back immediately. So the good thing about non-blocking is if you're polling, you say check, 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 and you want to go in a loop. You don't want a blocking interface because the first one you go, it'll wait until there's some data. Instead, you might want to poll through. Okay. Non-blocking is different from asynchronous. I like to think of asynchronous as the tell me later interface. A lot of devices can be put in an asynchronous mode. And what happens in an asynchronous mode is if I do a read, I say, here's a buffer, read 100 bytes for me. It returns immediately, but later it signals me to tell me it's done. Okay, that's asynchronous. So it completes everything I want, but it does it later. And it returns immediately because my read call in an asynchronous interface is an immediate setup, and then it returns right away because the thing is busy waiting. And then later, inside the kernel, and then later it comes back and says, oh, here's your data. Okay? So these are 3 possible ways of going at this. And in many cases, the same device that you open with open or fopen, you can then take, let's say with open, you can take that file descriptor and do an IOCTL on it that says make this non-blocking or make this asynchronous. You should take a look. You do man on IOCTRL, IOCTL, or however you want to pronounce it, and you can see how you can use flags on many of the devices to ask it to be non-blocking or asynchronous. Okay? And hopefully you can start to see where these other 2 might be very useful when you have a lot of stuff going on. You don't want to waste time blocking. Okay? Now, what's the alternative, by the way? Just here, this is a quick mental test. If I wanted to do blocking because I thought it was somehow cleaner and simpler, how could I get the effect of checking many things simultaneously while still blocking? Instead of, anybody think instead of one thread, I might have many threads, right? 1 thread per read call. Every one of them could be blocking, and, when something comes back, it wakes up. Okay. Good. So if you look, I showed you a more recent version of the Skylake processor at the beginning of the class, but I just wanted to get you again this idea that the processors, which are these little cores down here, are really kind of the most boring part. The chip architects, the CPU architects would disagree with me very strongly, but there's a very lot of cool stuff that isn't the core. Okay, and basically what we're talking about now is how do you control the rest of that stuff? Like, for instance, even this little tiny chip, which was made for laptops and whatever, has an integrated GPU. It's got enclaves, software guard extensions. It's got a bunch of caches. It's got several memory controllers. It's got PCI Express for graphics. It's got a DMI connection to the platform control hub. All of that stuff is not the cores. It's other stuff, which is I/O. The platform controller hub, which has this direct media interface with the processor, also controls all sorts of stuff. Okay, I/O like USB and Ethernet and lots of SATA disk drives and all that stuff. Okay, so you could kind of say that, yeah, the first half of this class was about the CPU and memory, but now we're getting somewhere, right? We've got I/O coming up. Okay, the interesting, I didn't say that. Actually, I'm a computer architect, so I'm kind of messing with you a little. But so really, a modern I/O system, one of the ways of looking at this is many buses with lots of I/O devices hanging off of it, and part of the process of controlling things is figuring out kind of how to reach out to these devices and talk to them across these buses. And so, for instance, the PCI bus, which you've probably plugged cards into a computer before, oftentimes has sort of a bridge from the CPU to a couple of different buses. And then, for instance, the PCI bus, which is a modern bus, might have a bridge to an ISA bus, which is a really old school IBM bus, and you can actually have legacy keyboards and mice and so on. And then the PCI bridges might actually talk to a USB controller, which then you can plug your USB memory sticks and all the USB headphones and stuff you're used to, or a SATA controller that you can put your scanners and hard disks. You know, normally you don't have to worry about this stuff, but if you were an operating system designer at the lowest level and dealing about boot, what happens at boot time is, for instance, the CPU reaches out and talks to the USB controller and starts enumerating all the devices to figure out what is out there, and then puts them in a certain order so they're ready to go. So that's part of the boot process. Okay? Now, you're not going to have to enumerate USB devices in this class, but I just wanted to give you an idea that some of that happens. Okay, it's very interesting. The other thing that's kind of interesting, this is a very old slide now, but it still's got the point. Many orders of magnitude, like maybe 12 or more, 14, 15 these days, of data rates between the keyboard, okay, and the fastest system buses, right? The keyboard is way down here, number of words per minute, and the system bus is in hundreds of gigabytes per second. Okay, very different ranges. And the reason I point this out, 12 orders of magnitude, 16 orders of magnitude, whatever it currently is, the reason that's so hard is because how do I service packets at this rate or whatever, and at this rate without wasting a bunch of time at the low end or missing a bunch of stuff at the high end? So I've got to somehow set this up so that I can make it work. And of course, one of the ways we do that is things that are unpredictable or very slow, we use interrupts. Makes sense, right? A keyboard press causes an interrupt which goes in and grabs the keys. Some of this higher priority stuff, maybe the first packet that comes in, higher priority, higher speed, first packet that comes in generates an interrupt, but if we generate an interrupt for every packet coming off of a 100 gigabyte network, gigabit per second network, we'd miss every other packet at least. So what happens is the first one comes in, generates an interrupt, and then I pull, and I have to pull in all the packets that happen to be received in the time it took the interrupt to occur. Okay? So, again, you don't necessarily need to write these levels of device drivers in this class in the projects, but I wanted to give you a flavor for the interesting spread in data rates you got to deal with. Okay? And so let's talk about something simple. For instance, if somebody were to ask you at a party, again, I'm trying to help you with your social life here. How does the processor talk to the device? What are you going to say? Well, you might say, I know that CPU talks to memory through a memory bus, and maybe there are some adapters. For instance, the CPU talks through an adapter to a device, and maybe there's an interrupt controller. So you now have some of the pieces, but bottom line is, in order to have a device, there's some controller somewhere on the other end of the bus that really manages the device directly. Okay, so here's an example of maybe a screen that has a device controller and a bunch of interfaces and registers and memory. And for instance, this CPU might interact with addressable memory, which when you write a byte in that addressable memory, it automatically puts a bit on the screen. Or when you write a byte in this addressable memory, it causes a rectangle, or a triangle to be drawn as part of your game. Okay, so just the act of writing memory that doesn't go into DRAM, but rather goes into a set of physical addresses that are in a device controller, just that act of writing causes something to happen. That's called memory mapped I/O. Okay, and it's the simplest type of interface. I read and I write addresses that are in the physical address space, and it causes hardware to do something. Okay, so you can have memory for requests, queues, like I can put a bunch of objects to be drawn on the screen. I could put bitmapped images. By reading and writing some of the control registers, I could cause the screen to be cleared. I could cause my images to move. There's all sorts of stuff. Okay, and regardless of the complexity of this connection in buses, there's really two ways that we like to think of in terms of how do we talk to I/O. One is I/O instructions. So some processors like Intel have the ability to execute in and out instructions which read and write these registers, and memory mapped I/O where you just do loads and stores. And those loads and stores map to physical addresses that end up reading and writing and causing the I/O to happen. Okay, so memory mapped I/O, by the way, is the most universal, pretty much available on all processors. And all I've done is I've taken this device, mapped it into the physical space. I could set up my page tables to point at it, and suddenly I could read and write addresses that cause the screen to draw. Okay? So, for instance, what that really means is here's a set of physical addresses that do stuff, and so if I write up here, I might actually put commands to draw in the display, or if I write here, I might actually just put dots on the display. Okay? All right. Everybody with me on memory map? So the idea is when I read and write memory, I'm causing commands to happen. Very simple. Okay. So, and by the way, because it's memory, I can use address translation and I can protect it. So I could give a user process full control over a graphics controller by mapping the command addresses of that device into the user's address space with the page table, and now suddenly they can read and write virtual addresses that cause the device to change. Okay. Now, the other thing, and I'm going to we'll finish up here very quickly, but we can also transfer data to and from the controller with something called programmed I/O, where in this situation, if I read an address from the device, I can read 1 byte at a time, and if I write 1 byte at a time, I can go back to the controller. But you can imagine that if that's a disk drive, reading every byte out of the disk drive by going in a loop, read, might take a long time with the disk. Okay, but that's called programmed I/O. The other option, which we'll talk about when you guys, when we reconvene next time, is direct memory access, where I actually set up a part of the hardware to do that transferring for me, and it'll be a lot faster than me reading individually. Okay, and I don't have time for that right now, so we will. I want to give you an in conclusion. We've started talking about many different I/O devices, different speeds, everything from 0.1 bytes per second to gigabytes per second, hundreds of gigabytes per second. Many different access patterns, block devices, character devices, network devices. Different access timing, blocking, non-blocking, asynchronous. We talked about I/O controllers, which are the thing that directly controls the I/O devices. And we started talking, we're going to be talking more about interrupts and polling next time. So I'm going to wish you all a nice spring break. Try not to forget everything from 162. Other classes, it's okay. I guess like 61B, you can forget some things from there. But 162, keep it all in your brain. And have a great spring break. We will see you on the other side.
Why don't you email me the details about what you need for a letter, and then I'll be happy to supervise you, and let's hook up after spring break. Okay. I'll tell you what, send me details of what needs to be in there, and I'll try to get it to you. So when tomorrow? Okay, and do you need to email it to them before then, or what's this? Send me the details, and we'll do my best to get you something. It'll probably be short. But if what it needs to be is a statement that I'm happy to supervise you, that's certainly true. It's got to happen in the next hour or something. You can send it to me so that it's there when I get home. I'll see what I can do. And it'll be, as long as it's okay, it'll be really short, and I can tell them they're welcome to call me or something. But let me know what's supposed to be in this letter in terms of, is it actually a recommendation or just a statement that I'm more than happy to work with you. So draft me a couple of sentences so I know what you're listening. But I'm more than happy to work on you with this. Sorry about the way the term went so far.